How many numbers would you need to describe the moon? That might sound like a strange question, but pause for a moment and consider it. To map every crater on its surface, you would need at least 2 coordinates, latitude and longitude, for each. Then there is the size of every crater, its depth, its shape. That alone brings us to thousands of numbers. Add to that the chemical composition of the surface, the mineral content, the temperature variations across different regions, and soon, those thousands become millions. All to describe one small rocky body circling our planet. Now, imagine trying to do the same for a planet, or a star, or a swirling nebula stretching across light years of space. The complexity increases beyond measure. Every structure in the cosmos seems to demand countless parameters to be defined, cataloged, and understood. And yet, there is one class of object in the universe that breaks this pattern, a kind of cosmic paradox. These are the most extreme, most powerful objects known to physics. And yet, to describe them fully, you only need 3 numbers. Not 3 million. Just 3. Welcome to the strange and beautiful simplicity of black holes. To describe even the most familiar objects in our night sky requires an overwhelming amount of information. Take the moon, for instance. At first glance, it is just a gray, cratered sphere suspended in the sky. But any serious attempt to model its surface requires a vast library of data. Thousands of impact craters, each with unique coordinates, depths, diameters, and ridge features, must be logged. There are variations in surface reflectivity, shadowing, and age estimates based on erosion. Some regions are composed of basaltic plains, while others hold anorthositic highlands. Every square kilometer presents its own microscopic secrets. Extend this attention to detail beyond the moon and into the domain of planets. Consider Earth. Our own home contains mountains, oceans, deserts, rivers, weather patterns, tectonic plates, magnetic fields, and an atmosphere in constant motion. Add to that the biological complexity, billions of species, ecosystems, and evolving life forms, and the task of fully describing Earth becomes incomprehensible. One must account for atmosphere composition, greenhouse gases, temperature gradients, oceanic salinity, cloud behavior, and seasonal shifts. The numbers quickly expand from millions to billions to the unknowable. Gas giants like Jupiter add new layers of complexity. With no solid surface, their atmospheric layers swirl in bands of different colors, speeds, and compositions. Violent storms like the Great Red Spot can last for centuries. Beneath the clouds lie deep layers of metallic hydrogen, crushing pressures, and possible rocky cores. Each parameter, from temperature at specific altitudes to the velocity of jet streams, adds yet another dimension to the descriptive challenge. Even the magnetic field of Jupiter, 20,000 times stronger than Earth's, pulses with variables that stretch computational models. Move farther out, and the challenges multiply. Stars, for example, are far from simple glowing spheres. They live complex, evolving lives. Their spectra vary by temperature, chemical makeup, and rotational velocity. They pulse, flare, and oscillate. Some stars exist in binary systems, influencing each other's evolution through tides, radiation, and mass exchange. Others are part of dense clusters or chaotic galactic arms, surrounded by interstellar gas and dust. To capture even one moment of a star's life requires a staggering number of measurements: luminosity, mass, age, composition, core pressure, and fusion rate, to name just a few. And then there are nebulae, the great clouds of dust and gas, birthplaces of stars. These sprawling structures span dozens or even hundreds of light years, with intricate filaments shaped by turbulence, magnetism, and radiation. They possess cold pockets of star-forming material, ionized regions glowing under the blast of young stars, and shock waves from ancient supernovae. Their shape and brightness evolve over time, demanding constant observation from many different wavelengths: infrared, ultraviolet, X-ray, and radio. Describing even a fraction of a nebula is a project fit for entire teams of astrophysicists over decades. In short, the more we try to understand the universe, the more the required numbers multiply. Every object, every structure, every chemical trace adds layers of complexity. The moon alone demands thousands of data points. Planets require billions. Stars, nebulae, galaxies. Each demands more than our minds can intuitively grasp. This is the expected rule in astrophysics. To describe something completely, you must collect almost endless information. But just when you are prepared to surrender to this complexity, you encounter an object that breaks every rule, an object that asks for only 3 numbers. In a universe where every known object seems to demand millions of details to describe fully, black holes stand apart, utterly alien in their simplicity. While the moon requires an atlas of craters and Earth, a symphony of climatic and geological data, a black hole can be completely defined by only 3 numbers. Not 3,000, not 3 million, only 3. These are mass, electric charge, and angular momentum, properties that, together, determine the shape and behavior of a black hole in its entirety. No more detail is required. No less will do. The idea is deeply counterintuitive. A star might collapse into a black hole after a chaotic life of fusion, rotation, and violent death. Another might be born from a merger of 2 neutron stars. A third might slowly grow over billions of years, swallowing gas and entire planets. Each formation path is different. Each history is rich with variation. And yet, when the black hole settles into equilibrium, all those differences vanish behind the event horizon. The black hole becomes a blank slate, revealing nothing about what came before, except, astonishingly, its mass, its charge, and its spin. This remarkable property of black holes is formalized in what is known as the no-hair theorem. Coined by the American physicist John Wheeler, the phrase "black holes have no hair" means that black holes lack any distinguishing features. They do not retain scars from their formation. They have no geological fingerprints. They do not carry memories of the stars, dust, or data that once composed them. If two black holes have the same mass, the same charge, and the same angular momentum, then they are indistinguishable in every possible way, no matter how different their origins may have been. Imagine compressing an entire encyclopedia into a single black hole. Every fact, every page, every diagram, lost to the collapse. Now imagine doing the same with a supercomputer, or a library, or the combined data from every civilization across the galaxy. No matter what information is thrown into a black hole, the result is always the same. 3 numbers. The complexity of the cosmos reduced to a mathematical trinity. The information, it seems, is not only hidden, it is erased. Or is it? Here lies one of the greatest puzzles in modern physics. If black holes can form from anything, how can they be described by so little? Where has all the other information gone? Is it destroyed in violation of the sacred principles of quantum mechanics? Or is it somehow encoded in a form we do not yet understand? This question is not just academic. It strikes at the heart of how we understand reality itself. Can the universe truly forget? Can it throw away data? Or have we simply not learned how to read what remains? And so black holes, these apparently simple objects, become philosophical provocations. They are defined by less information than a human face, yet they might contain more than any library ever could. Mass, charge, spin. These are the 3 sacred numbers that define them. But beneath that simplicity lies a vast unknown. To many physicists, this contradiction between the elegance of description and the chaos of origin is what makes black holes not only fascinating, but also essential to unlocking the deeper structure of the universe. Long before the term black hole entered the scientific lexicon, the idea of an object so dense that even light could not escape had already taken root. In the late 18th century, an English country parson named John Michell contemplated an intriguing possibility. If light were made of particles, as Isaac Newton believed, then perhaps it could be pulled by gravity like any other form of matter. Michell proposed that if a star were massive enough and compact enough, its escape velocity could exceed the speed of light. In such a case, the star would be invisible, a dark star, as he called it. At the time, Michell's idea seemed more like a mathematical curiosity than a prediction about the physical universe. It lacked experimental support and quickly faded into obscurity. But his insight planted a seed. Over a century later, in the midst of war-torn Europe, another mind would pick up the thread. In the trenches of the First World War, German physicist Karl Schwarzschild discovered the first exact solution to Albert Einstein's newly published equations of general relativity. His goal was simple: to understand how space and time behaved around a perfectly spherical mass. Schwarzschild's solution revealed something profound. According to the mathematics, there existed a critical radius around a massive object where the curvature of space-time became infinite. This radius, now known as the Schwarzschild radius, defined the event horizon, the invisible boundary from which nothing, not even light, could escape. Although Schwarzschild himself died shortly after his discovery, his solution stood as a mathematical doorway into a new and strange realm of gravity. Still, few at the time grasped its implications. The concept of a black hole remained a theoretical oddity. Throughout the early 20th century, Einstein's theory of general relativity gained admiration for its elegance, but was seen as disconnected from experimental physics. Quantum mechanics dominated the attention of physicists, offering real-world predictions and laboratory confirmations. Gravity, in contrast, became a backwater field, elegant, beautiful, but largely irrelevant to the everyday workings of matter and energy. Many considered the strange infinities predicted by general relativity to be mathematical artifacts rather than physical realities. But the groundwork had been laid. As the decades progressed, scientists began to revisit Schwarzschild's solution with renewed curiosity. In the 1960s, Roger Penrose and Stephen Hawking would go on to prove that under very general conditions, the collapse of massive objects under gravity must lead to singularities, regions of infinite density. These results elevated the black hole from a mathematical curiosity to a physical inevitability. What had once been an idea scribbled in the notebook of a country parson had become a central focus of modern astrophysics. The path from Michel's dark star to Schwarzschild's radius to the modern black hole is a story of bold speculation, forgotten ideas, and triumphant returns. It is a story where imagination precedes mathematics, and mathematics precedes observation. Today, black holes are no longer fringe ideas, but fundamental features of our cosmic understanding. They shape galaxies, fuel quasars, and bend the very fabric of space and time. But it all began with a simple question. What if gravity could trap even light? By the middle of the 20th century, black holes remained little more than mathematical curiosities. The equations of general relativity predicted them, yes, but most physicists were focused on the dazzling rise of quantum mechanics, atomic physics, and particle accelerators. Gravity, slow and stubborn, seemed like an old theory with no new surprises. Even Albert Einstein himself was skeptical. He believed that nature would somehow prevent the formation of true singularities. To many scientists, black holes were mathematical ghosts that would never manifest in the real universe. But this skepticism began to fade in the late 1960s, when a wave of new thinking collided with fresh observational data. On one side, mathematicians like Roger Penrose were uncovering the strange implications hidden within Einstein's equations. Penrose proved that under realistic and general conditions, the gravitational collapse of massive objects was inevitable. Singularities were not exotic exceptions. They were built into the fabric of space-time itself. The concept of a black hole was no longer a possibility. It became a necessity. At the same time, a young physicist named Stephen Hawking joined the conversation. Diagnosed with a degenerative disease and given little time to live, Hawking dove into the mathematics of general relativity with brilliant intensity. Collaborating with Penrose, he helped establish theorems showing that singularities must occur not only in the collapse of stars, but even at the beginning of the universe itself. Hawking did not just change our understanding of black holes, he transformed our view of space and time. His work placed black holes at the center of modern cosmology. While theory evolved rapidly, the skies began to tell their own story. In the early 1970s, astronomers operating new X-ray telescopes detected an unusually strong and compact source of radiation in the constellation of Cygnus. This source, later named Cygnus X1, displayed characteristics no ordinary star could explain. The X-rays appeared to come from matter spiraling into an invisible, massive object. There was only one reasonable explanation. A stellar mass black hole was feeding on its companion star, releasing enormous energy in the process. This marked a turning point. Black holes were no longer abstract solutions on paper. They were real entities, casting shadows in the cosmos. Observational astrophysics caught up with theoretical predictions. New instruments, particularly those launched into orbit, began to reveal an X-ray sky far richer and more violent than imagined. Over the decades, dozens and then hundreds of black hole candidates were identified. Many existed in binary systems. Others sat at the hearts of galaxies, consuming matter and lighting up the cosmos as quasars and radio jets. From the trenches of war to the silence of distant galaxies, black holes had returned with a vengeance. Once neglected and doubted, they became central to the story of the universe. They taught us that space can bend so sharply it breaks, that time can end at a point, and that the cosmos still holds secrets more exotic than fiction. The black hole renaissance had begun, and it was only the beginning. In the vast diversity of the universe, no two things are ever exactly the same. Every star, every planet, every moon is marked by a unique history. Craters, fractures, fields, atmospheres, and chemical imprints that tell the story of how it formed, what it encountered, and what it has become. Even the face of a human being, though shaped by a common pattern, is defined by countless subtle variables: freckles, wrinkles, scars, expressions. Nature seems to favor complexity, variety, and detail in all its creations, except, curiously, in the case of black holes. Black holes are the great exceptions to this cosmic rule. According to the no-hair theorem in general relativity, all black holes, regardless of their origin, are completely described by only three quantities: mass, electric charge, and angular momentum. That is all. If two black holes share the same values for these three properties, they are fundamentally indistinguishable. It does not matter whether one was formed from a supernova and the other from a galactic collapse. Their physical characteristics will be identical. Everything else, every molecule, memory, or mechanism that led to their formation, is lost to the outside world. This profound simplicity is why physicist John Wheeler famously said, "Black holes have no hair." In this context, hair refers to the fine, distinguishing details, those markers of individuality that other celestial objects wear like fingerprints. A neutron star may retain a memory of its magnetic field structure, its thermal gradient, or the internal stiffness of its matter. A gas cloud holds turbulence, motion, and gradients, but a black hole is bald. It carries no record of what fell in. It does not display any surface features or spectral identity. It is a blank, pure solution of space-time. This realization is both beautiful and troubling. It means that black holes are the simplest large-scale objects in the universe. They do not need 1,000 variables to describe them. They need only 3. And yet, it also means that black holes erase history. A million-page encyclopedia thrown into a black hole produces no more external difference than a single paperclip. Whether you feed it stars, data, machines, or light, the result is always the same. A slightly larger mass, possibly more spin, and the same eerie silence. Physicists struggled with this idea for decades. After all, it seemed to violate one of the core principles of quantum mechanics, that information is never truly lost. Quantum theory teaches us that every system evolves in a way that, at least in principle, is reversible. Even the most chaotic chemical reaction can, in theory, be traced backwards step by step. But in black holes, the process appears one way. You can observe what goes in, but never retrieve what was there. If that information is truly lost, then something deep within physics is broken. The uniqueness theorem makes black holes feel strangely artificial, like constructs built for a mathematical experiment rather than natural objects. But observations have confirmed their presence across the universe. They exist, and they obey this rule. The simplicity is not a flaw in theory, it is a feature of reality. Black holes stand as monuments to the idea that beneath the wild patterns of the universe, there may lie structures of astonishing elegance. The challenge now is to understand how this elegance connects to the deeper laws of nature, and whether that lost hair is truly gone, or merely hidden. In the everyday world, we do not think in equations. We think in sensations. A cold breeze, a warm drink, a stifling room, all are expressions of thermodynamics, the science of heat, temperature, and energy flow. Behind every warm gust of air or melting block of ice lies a dance of molecules. Gases are made of particles in motion, bouncing, colliding, exchanging energy. And despite the chaos, thermodynamics allows us to describe them with just a few variables: temperature, pressure, and volume. These macroscopic numbers summarize an astonishing number of microscopic details. One of the key concepts in thermodynamics is entropy. Though often misunderstood, entropy is not just about disorder or decay. It is a measure of how many possible internal arrangements a system can have, while maintaining the same external conditions. A container of gas at a given pressure and temperature might contain trillions upon trillions of molecules, each zipping around in its own direction, yet all combining to create the same measurable outcome. Entropy counts the number of these invisible configurations. The more options there are, the higher the entropy. Now imagine mixing a cup of hot tea with a cup of cold tea. The result is lukewarm. Simple, yes, but also irreversible. You can stir and wait forever, and the two cups will never unmix. The entropy of the system increases, and that increase is permanent. This is the second law of thermodynamics, and it is as close to sacred as any principle in physics. The total entropy of a closed system never decreases. It defines the direction of time and the arrow of cause and effect. Once entropy increases, it cannot go back. But what happens when that cup of tea is thrown into a black hole? This was the thought that haunted physicist Jacob Bekenstein in the early 1970s. If the mixed tea increased entropy, and that entropy vanished into a black hole, did the universe just lose information? Did the total entropy decrease? That would violate the second law. And yet, according to classical general relativity, a black hole has no memory of what falls in. It does not seem to carry entropy in any meaningful way. The contradiction was sharp and unsettling. Bekenstein proposed a bold solution. Perhaps black holes do have entropy, but not the usual kind. He suggested that the entropy of a black hole is proportional not to its volume, like in gases, but to the surface area of its event horizon. This was a radical idea, that the boundary of a black hole, not its interior, stores information. At first, the notion seemed speculative, but then came Stephen Hawking, who took Bekenstein's suggestion and pushed it further. By applying quantum mechanics near the event horizon, he discovered that black holes are not perfectly black. They radiate heat. This radiation, now called Hawking radiation, meant that black holes have a temperature. And if they have a temperature, they must also have entropy. Hawking confirmed Bekenstein's intuition. The entropy of a black hole grows with the square of its mass and is tied to the surface area of its horizon. A black hole, once thought to be a dead end of physics, was now a thermodynamic object. It had heat, entropy, and an arrow of time. The implications were staggering. Somehow, the deepest ideas of thermodynamics had found their way into the cold, silent hearts of collapsed stars. For centuries, black holes were imagined as cosmic sinks, regions from which nothing could return, not even light. Their very name suggests a perfect prison of gravity, a region of eternal silence and one-way fate. But in the 1970s, Stephen Hawking challenged that picture with one of the most unexpected and revolutionary insights in modern physics. He showed that black holes are not completely black. They emit radiation, faint, cold, but real. And from this quiet whisper of heat came a deep paradox that shook the foundations of science. The source of this radiation is not inside the black hole, but rather just outside the event horizon. According to quantum mechanics, even the emptiest vacuum is not truly empty. It boils with fluctuations, brief appearances of particle-antiparticle pairs that pop into existence and quickly annihilate each other. Normally, these virtual particles vanish before they can be seen or measured. But near the event horizon, something unusual can happen. One particle may fall into the black hole, while the other escapes into space. The escapee becomes real. The black hole loses a tiny bit of mass. This process is subtle but relentless. Each escaping particle reduces the black hole's energy, and by Einstein's relation between mass and energy, the black hole becomes slightly lighter. Over vast amounts of time, this process continues. The black hole radiates away its mass, slowly shrinking. The temperature of this radiation, known as Hawking radiation, depends inversely on the black hole's mass. The larger the black hole, the colder it is. A black hole with the mass of a star radiates at a temperature barely above absolute zero. This temperature is far too faint for any current telescope to detect, and yet, its existence is a turning point in physics. It tells us that black holes obey the same laws of thermodynamics that govern tea kettles, furnaces, and stars. They are not just exotic ends to a cosmic story. They are thermodynamic engines. They have temperature. They lose energy. They change with time. Hawking's insight transformed black holes from eternal static objects into dynamic and evolving entities. But with this new radiation came a new problem. If a black hole radiates away all its mass, then eventually it must disappear. And if it disappears, what happens to all the information that fell into it? From a physical standpoint, the escaping particles carry no record of what entered the black hole. They form a perfect thermal spectrum, featureless and generic. The encyclopedia, the tea, the planet, they all vanish, replaced by particles with no story. This is the infamous black hole information paradox. In ordinary physics, information is conserved. Even if a process is messy or irreversible, the fundamental details remain, hidden in correlations or entanglements. But Hawking radiation seemed to break that rule. It hinted that the universe could lose information forever. That cause could become disconnected from effect. Physicists have debated this question for decades. Some believe the information escapes in a hidden form. Others suspect new laws of physics are needed. But all agree on one thing. Hawking radiation opened a door that can never be closed. Thanks to Hawking's work, we now see black holes not as final voids, but as glowing remnants of collapsed matter, slowly evaporating into the fabric of space. They may be dark, but they are not silent. Their whispers may hold the keys to reconciling quantum mechanics with gravity, to a deeper, unified understanding of nature. The most mysterious objects in the cosmos are, paradoxically, shedding light. When Stephen Hawking discovered that black holes emit radiation and slowly evaporate, it solved one mystery and created a much deeper one. If a black hole disappears, what happens to everything it once contained? Imagine throwing a book into a fire. The pages burn, the letters vanish, but in principle, the information remains, dispersed in heat, ash, and smoke. But when something falls into a black hole, and the black hole evaporates into pure thermal radiation, it seems that the information is not just scattered, it is destroyed. This is the heart of the information paradox. In the language of quantum mechanics, information can never be truly lost. The evolution of any system, no matter how chaotic, is governed by reversible equations. Even if you cannot practically reverse the process, the laws of physics insist that the final state of a system must contain, in some subtle way, all the information about its initial conditions. This idea is not a minor detail. It is foundational to quantum theory. If information can be lost in black holes, then quantum mechanics itself must be incomplete or broken. But general relativity tells a different story. According to classical gravity, nothing that crosses the event horizon of a black hole can ever return. The horizon acts as a one-way membrane. Whatever enters is trapped, and the internal structure is shielded from the rest of the universe. When the black hole evaporates completely through Hawking radiation, all that remains is a featureless cloud of particles. No fingerprint, no record, no remnant of the fallen matter. The information appears to be gone forever. This contradiction between quantum mechanics and general relativity is not just a technical issue. It is a clash between two of the most successful theories in all of physics. One insists that information is conserved. The other seems to permit its erasure. The tension is so deep that many physicists consider resolving the information paradox to be one of the most important steps toward unifying the laws of nature. To solve it may require a complete theory of quantum gravity, a framework that does not yet exist. Over the decades, many ideas have been proposed. Some physicists suggest that the information is encoded in subtle correlations between the outgoing Hawking particles. Others propose that remnants of the black hole remain after evaporation, storing the lost data. A more radical idea, known as the firewall hypothesis, argues that the event horizon is not smooth and passive, but a violent wall of quantum energy that burns information as it enters. Each of these ideas tries to reconcile the paradox, but none have been universally accepted. In recent years, attention has turned to a new and powerful idea, the holographic principle. It proposes that all the information about what falls into a black hole is not lost, but stored on its surface, encoded on the horizon itself, like a cosmic recording. In this view, the three-dimensional interior is a kind of illusion, and reality is written on the two-dimensional boundary. This strange but elegant concept may hold the key to resolving the paradox. Perhaps the information is never lost. It just hides in plain sight, etched into the very skin of space-time. In the wake of the information paradox, physicists began searching for deeper principles, ideas that could reconcile the strange thermodynamics of black holes with the unshakable laws of quantum mechanics. What they found was something astonishing, a bold proposal that seemed too strange to be true and yet too elegant to ignore. It is known as the holographic principle. At its core, it suggests that all the information contained within a region of space can be fully described by information encoded on its boundary, just like a hologram. To understand this, imagine a security hologram on a credit card. The image appears three-dimensional, but it is actually stored in two. The depth, shape, and shading you see are illusions, projections of information flattened onto a surface. The holographic principle suggests that our universe might work the same way. A black hole, which appears as a three-dimensional object with depth and interior, could be fully described by the two-dimensional surface of its event horizon. Not metaphorically, but literally. Every detail inside is encoded outside. The first clue to this idea came from the strange behavior of black hole entropy. Unlike ordinary objects, whose entropy scales with volume, the entropy of a black hole scales with its surface area. The more massive the black hole, the larger the area of its horizon, and the greater its entropy. This observation led to a radical thought. Perhaps black holes do not store information within their interiors, but on their surfaces. And if that is true for black holes, could it also be true for the entire universe? This question led to one of the most powerful developments in modern theoretical physics, the ADS-CFT correspondence. It proposes that a gravitational theory in a higher dimensional space is exactly equivalent to a quantum field theory on a lower dimensional boundary. In this framework, gravity becomes an emergent illusion. The true dynamics are written on the edges, like shadows cast on a wall. The bulk and the boundary are different languages describing the same reality. It is a mathematical bridge, gravity on one side, quantum mechanics on the other. The holographic principle turns black holes into cosmic mirrors. What falls in is not lost, but inscribed, pixel by pixel, onto the surface. Like a hard drive encoding vast amounts of data in a thin layer, the event horizon may hold every detail of what entered. If this is correct, then the answer to the information paradox is already there, hidden in the horizon's subtle patterns. The black hole, once thought to be a tomb for knowledge, becomes instead a librarian of the cosmos, quiet, unreadable, but not forgetful. What truly lies inside a black hole? It is a question that has haunted physicists and philosophers alike. The outside of a black hole, defined by its event horizon, is mathematically elegant and surprisingly simple. But beyond that veil lies something far stranger. According to general relativity, all paths within the horizon lead to a singularity, a point of infinite density where space-time curves without bound and the laws of classical physics cease to function. It is not just a place that is hard to reach. It is a place where our understanding of reality itself breaks down. Unlike any other object in the cosmos, the interior of a black hole is sealed from view, not by distance, but by principle. No signal, no light, no message can travel from the inside back out. This makes it fundamentally unobservable. You could fall into a black hole and record your experiences, but those experiences could never be shared with the outside world. From the perspective of science, which depends on measurement and repeatability, this makes the interior of a black hole the ultimate mystery, forever hidden behind an uncrossable line. Still, mathematics offers a path where observation cannot. Theoretical physicists construct models, simplified versions of black holes, often in higher dimensions or within string theory, that allow calculations of their internal structure. In some of these models, black holes are not empty voids, but complex systems filled with tangled fields, branes, or quantum geometries. One famous example is the Strominger-Vafa model, which used string theory to count the internal microstates of certain highly symmetrical black holes, and found a match with the predicted entropy. It was a glimpse behind the curtain. Yet, even with these insights, the real interiors of astrophysical black holes, like those at the centers of galaxies, remain out of reach. We do not know if space-time truly ends at a singularity, or if quantum gravity somehow resolves it into something finite and structured. Some theories suggest a bounce into another universe. Others speak of quantum fuzz replacing the classical core. But until a complete theory of quantum gravity emerges, we are left with conjecture. The center of a black hole is not just a place. It is a question that physics is still learning how to ask. Perhaps the most profound realization is this: what is inside a black hole might not be inside at all. If the holographic principle holds, then everything that ever fell into the black hole is encoded on its surface. The interior is a projection, an emergent feature woven from boundary data. In this view, black holes are not just astrophysical curiosities, they are windows into a deeper language of nature, where space, time, and even dimensionality are not fundamental, but born from more primal information. The truth inside a black hole may not be hidden in its center, but written across its edge. Science has always been a balance between two powers, the hand of experiment and the eye of theory. One reaches outward, gathering data, testing hypotheses, and anchoring us in the physical world. The other reaches inward, building vast mathematical structures to describe what cannot yet be touched. In most branches of physics, these two move in tandem. Observations inspire theories, and theories predict observations. But with black holes, the scale tilts. The experiment stops at the edge of the event horizon. Beyond that, mathematics stands alone. No signal can escape a black hole once it crosses the event horizon. No probe, no photon, no message. This is not a technological limitation. It is a fundamental feature of space-time itself. In principle, we could drop a spacecraft into a black hole with instruments tuned to study its core, but the data would never return. Even if it transmitted at the speed of light, the signal would curve inward forever, lost to the singularity. What lies inside, therefore, cannot be measured directly. Our tools remain forever outside the gate. So physicists turn to thought experiments, to pen and paper universes built on assumptions and symmetry. These idealized models may not reflect the messy details of real black holes, but they offer clarity and control. In string theory, in loop quantum gravity, and in toy universes with extra dimensions, black holes become solvable. The inner workings are mapped out, microstates are counted, entropy is derived, quantum effects are simulated. But the question always lingers. Do these simplified black holes reflect reality, or are they just shadows of our mathematical desires? Some scientists argue that reality may always stay a step ahead of us, that the black hole interior is not just hidden, but unknowable in a deeper sense, that our minds, shaped by cause and effect, cannot fully grasp what lies beyond causality. Others remain hopeful, believing that the right unification of quantum theory and gravity will reveal not just the inside of black holes, but the fundamental architecture of space and time itself. In that view, black holes are not barriers, but bridges, gateways to new physics. Until then, we are left with a strange irony. Black holes are among the most physically real objects in the universe. We can observe their gravitational pull, witness their mergers, and detect their waves rippling through space-time. And yet, their interiors remain the most abstract, the most theoretical, the most distant from experiment. We see the outlines, but not the core. We map the horizon, but not the heart. In black holes, the dream of physics meets its deepest challenge: to know what can never be seen. Black holes began as mathematical oddities, phantoms born from equations rather than observations. For centuries, they lived in the margins of theory, whispered about by a few bold thinkers, but largely ignored by mainstream science. And yet, today, they are among the most profound and confirmed realities of our cosmos. We have seen their gravitational grip on stars. We have heard their collisions echo across space-time as gravitational waves, and we have even photographed the shadows they cast upon the glowing matter around them. They are no longer ghosts. They are anchors of reality. But black holes remain paradoxes. They are simple in definition, yet unfathomable in consequence. Described entirely by three numbers: mass, charge, and spin, they still swallow whole histories of stars, planets, and information. They emit radiation, yet conceal their insides. They are governed by gravity, but demand the language of quantum mechanics to be understood. And somewhere between those opposing forces, they point toward a deeper truth. A truth not just about astrophysics, but about the nature of existence itself. Perhaps what makes black holes so haunting is not what they reveal, but what they conceal. Every discovery we make about them leads to more fundamental questions. If information is not lost, where is it? If entropy is written on the surface, What does that say about the structure of space? If horizons encode interiors, might the universe itself be a hologram? These questions do not have final answers, not yet. But they stretch the imagination, and they stretch the science, forcing us to look at reality through new, more humble eyes. In a way, black holes are mirrors. They reflect our intellectual limits and challenge our desire for certainty. They are the edge of our knowledge, regions where equations break, intuition fails, and observation is silenced. And yet, they inspire more than doubt. They invite awe. Within their darkness lies the promise of understanding, not just of collapsed stars, but of the laws that built the universe itself. To study black holes is to stare into a mystery, and to accept that we may be shaped by what we cannot yet see. As we move forward, guided by theory, by experiment, and by hope, black holes will remain among the most powerful laboratories in nature. Not in the traditional sense, with beakers and switches, but as cosmic thought experiments brought to life. They compress time, distort space, and challenge meaning. And perhaps one day, through them, we will arrive at a theory that unifies everything, a framework where gravity and quantum dance as one. Until then, the black hole waits, silent as ever, holding the answers just beyond the event horizon. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.